Let us get back to our image, illustration, 3D image here. So now your z is bounded between square root of 4 minus x squared, negative and positive. So your z is bounded between negative square root of 4 minus x squared and square root of 4 minus x squared. Let us take the integral. So here we go. Here we have the integral, negative 2 to 2, negative square root of 4 minus x squared, square root of 4 minus x squared. And here you have the inner integral is with respect to y. So we can copy this down, x squared plus z squared. And here you have your inner integral, x squared plus z squared for dy, dz, and dx. Let us calculate this integral first. This is y. Y ranges between x squared plus z squared and 4. Let me erase this part. This is equal to integral minus 2 to 2, negative square root of 4 minus x squared to square root of 4 minus x squared. And here you have square root of x squared plus z squared and 4 minus x squared minus z squared dz dx. So dz dx. Well, take a look at this. Take a look at this double integral. So here you have dz and dx. It means that we can use polar coordinates in xz axis. So in xz system, xz, my x ranges between negative 2 and 2. Negative 2 and 2. My z ranges between negative square root of 4 minus x squared and positive square root of 4 minus x squared. So this is the negative one, and this is the top side. So this is this area. My x is in between minus 2 to 2, and my z is in between negative square root of 4 minus x squared and positive square root of 4 minus x squared. As you can see, I have this disk here, which is just a circular region. So your r is in between 0 to 2, and your theta is in between 0 to 2 pi. So here I have the integral 0 to 2 pi, integral 0 to 2, this is my theta, this is my r. And here I have square root of r squared, and here I have 4 minus r squared. Remember that since we are using the polar coordinates, it is r dr d theta. Very well. This is equal to zero to 2 pi, 0 to 2. I have r times r squared, and I distribute that for r squared minus r to the 4 dr d theta. This is equal to 2 pi, and here I have 4/3 r cubed minus a fifth r to the 5th power 0 to 2. So I have 2 pi times. If I plug in 2 here, I get 32 over 3 minus 32 over 5, which is equal to 2 pi over 15. And I have my 32, and here I have 2. So I have 4 128 pi divided by 50. Another example for you. So this example says, use a triple integral to find the volume of tetrahedron T bounded by the planes. So let me write the region down here for you. The planes x plus 2y plus z equals to 2, and x equals to 2y, x is 0, and z is 0. Perfect. Let us use a triple integral to evaluate this volume. So the triple integral of our function. So we usually write 1 or just dv. Now our goal is to find the boundaries for our triple integrals or iterated integrals. So very well. Let us begin by the first plane. The first plane in xy plane, so we're looking at the projection. Remember that we try to project this in xy plane, xz plane, yz plane, whichever makes it easier for us to calculate the triple integral. We're going to do that. We don't have any problem with z, but in xy plane, z is equal to 0. When z is equal to 0, you get x plus 2y equals to 2, or y is equal to 2 minus x divided by 2, or y equals to 1 minus x halves. And also you have x equals to 2y, or y equals to x divided by 2. Okay, we have these lines, and x is equal to 0. When x is 0, your y is 0. These are the information that they have, and they're trying to create our region in xy plane. Okay, let's take a look at this. What I have, x-axis, y-axis, 1 minus x divided by 2. My x is equal to 0, y is equal to 0. So if x is 0, you have 1. If x is equal to 2, you get 0. And x is equal to 2, you get 1. So you have 1. So this is your line, y equals to x over 2. And this line, y minus x divided by 2. It's going to be this line here. Okay. So here we go. This is our region. This is our region, T. So your T for x is bounded between 0 and 1. This is your x, and your y bounded between these two line segments. So the lower line segment is y equals to x halves, and your upper boundary is 1 minus x divided by 2. Okay, so this triple integral can be written this. Integral with respect to x, this is your outer integral, the inner integral with respect to y, and the inside integral is with respect to z. So dz, dy, and dx. For z, z is equal to 2 minus x minus 2y. Z is equal to 0. So 0 to 2 minus x minus 2y. Your y is in between x over 2, 1 minus x over 2, and your x ranges between 0 to 1. Very well. Let's take these integrals. The inner integral with respect to z, the middle integral, then the outer integral, 0 to 1. And here you have x over 2, 1 minus x over 2. And here you have, just circle this, you have 2 minus x minus 2y minus 0. We're not worried about 0. Dy, then dx. So this is equal to 0 to 1. So here you have 2y minus xy minus y squared. Y ranges between x halves, 1 minus x halves, then dx. Now let me erase this part. I need more space. This is equal to, if I plug in 1 minus x over 2, then x over 2, then try to simplify this, I get 0 to 1. If I plug in 1 minus x over 2, I have 2 times 1 minus x over 2 minus x times 1 minus x over 2 minus 1 minus x over 2 squared minus. Now we substitute the lower bound, which is lower limit 2 times x over 2 minus x times x over 2 minus x over 2 squared. Okay, let's put everything in parentheses. Then, after simplifying, we take the integral with respect to x. Very well. Here we have the integral 0 to 1. If I distribute 2, I get 2 minus x plus x squared over 2 minus 1 plus x, and let me see, minus x squared over 4. So here I have minus x plus x squared over 2 plus x squared over 4 and dx. Let us simplify this. We get 2 minus 1, which is 1. Then I have plus x minus x, and I get minus 2x. X squared plus x squared, I get 1x squared. And here I can cancel out these two, so I get plus x squared. And dx. Dx. This is equal to. So with respect to x, I have x minus x squared plus x cubed divided by 3. X ranges between 0 to 1 here. I'm not worried about 0 because I have x here. I get 1 minus 1 plus 1 over 3, which is, this is the volume of the tetrahedron bounded by these planes.